Good evening, all of you. So today we'll start the session. I think it's because public holiday that we are seeing very less numbers today. So nonetheless, we'll just start. So is my voice and video clear to all of you? Yeah, fine. Okay, so then we'll start. So somebody from here last had asked, right, for her, like they had some issue regarding the uploading of documents for examination. Was that clear? Or it's maybe somebody else? So anyway, the exam registration is till 15th of August, so you have roughly less than 1 week. So if you are planning to write the exam, please do register as soon as possible. And in case you feel any technical difficulties like uploading documents or any other issues, please email directly to NPTEL because those official things will be handled from there, so you can directly email them. And last week, people had also asked how the final exam will be. So the final exam will be an objective type examination. So max to max, you will be having fill in the blanks plus objectives. So that is the discussion so far, and it will most probably be a 3 to 2 hour exam. And once the exam pattern will be finalized, it will be intimated to you via email. So, and once the course tenure is over, you will get approximately 1 month or so to prepare. So, in that time, they will inform the exam details, the duration, the number of questions, and so on. So, now we will move on to today's session. So, is my screen visible to all of you? Can somebody confirm? Yeah. Okay. So since we are a very few people today, so first we will go through a recap of the summary or this whole thing what was for the second week. So have all of you seen the videos for week 2 and week 1? So if not, please go through them as soon as possible. So already 2 weeks are over, only 2 weeks more are remaining. So it's better that you start revising from now itself. So during the past week, we saw the oxidation or layering operation. So in the first week, it was told that in the fabrication of a wafer, there will be many processes like oxidation or layering. Then we will be doing heat treatment, we will be doing doping, patterning, and so on. So in this particular week, oxidation, doping, and patterning was discussed. So first we went on to what is oxidation, and in that especially what is dry oxidation, where silicon reacts with oxygen to form the SiO2 layer. Then we saw what is wet oxidation, where silicon reacted with steam to form SiO2 and hydrogen. And the oxide layer, this particular oxide layer grows by consuming the silicon substrate. And if we know the thickness of the oxide that has been formed, we will be able to understand what is the thickness of silicon that is consumed. That is given by D prime is approximately 1.88 D. So where D prime is the thickness of the oxide layer and D is the thickness of silicon that is consumed. We will be having such kind of questions during the examination. So then we saw different oxide growth regimes. We had thin oxide and thick oxides. So thin oxide means it will be usually less than 30 nanometers. So approximately we will be high. It has a lean approximately 1 to 100 nanometers, but usually it will be less than 30 nanometers. That's the case. Then it will be having a linear oxide growth rate. The thickness of the oxide will be proportional to time, and the growth rate will be constant. And this particular setup will be reaction controlled. On the other hand, when we are growing thicker oxides, that is from 0.01 microns to 1 microns, it has a parabolic growth rate and the thickness will be proportional to the square root of time. And also we can see from this particular curve that the thickness and or the growth rate goes on decreasing with time. So this is a diffusion controlled process. So what is meant by diffusion control and reaction control? Reaction control meaning that the diffusion species, that is the gas that is coming from outside, will react with the silicon, and that is the process that controls the oxide formation. On the other hand, in case of thick oxide, the diffusion rate, that is the diffusion rate of the species from the outside onto the silicon substrate, will control the oxide formation. And then we saw the different doping times. In the first week, we were particularly introduced to the doping, and here the second lecture is completely about doping. We saw the details of thermal diffusion as well as ion implantation. In thermal diffusion, it is a high temperature process, and the dopant sources will be solid, liquid, or gaseous. And here we can see that maximum concentration of the dopant will be on the surface. And thermal diffusion is characterized by two processes. First one is deposition, that is dopants will be deposited onto the surface, and then we have driving. Under high temperature, these species will be driven into the thickness of the substrate. Next is ion implantation. Here, the source will be in the form of ions, and these high energy ions will be impinged onto the surface of the substrate, and they will get embedded inside the substrate. So, this is a low temperature process, and therefore maximum concentration is at some depth, that is below the surface, and this particular depth is known as the range. Then we have thermal diffusion. In case of thermal diffusion, we already said that it is possible to use solid, liquid or gaseous sources, right? So in case of solid sources, the total concentration will be constant, and we can find out the concentration of these dopants at a particular depth x, and the time taken for the formation of that particular concentration using a Gaussian solution. So these are the two sets of equations that is used for these particular solid sources in case of thermal diffusion. And here D is the diffusion coefficient and D0 is a pre-exponent. EA is the activation energy for the diffusion of the dopant, KB is the Boltzmann's constant, and T is the temperature. And in case of liquid or gaseous sources, we have surface concentration is constant, and that particular equation will be governed by an error function solution. That is Cx of t, where x is the depth and t is the time. We can calculate the depth using an error function. So then we go on to the details of ion implantation. We have already told that this is a low temperature process and the maximum concentration occurs at a particular depth inside the substrate, and this particular region is termed as the range. And post implantation, what happens is there is the requirement of doing heat treatment or annealing to activate the dopants. So then we saw in the last lecture about the lithography process. Lithography process overview is particularly important because lithography is that particular step that allows the miniaturization of devices. So in every year there is a miniaturization of the patterns that are available on a wafer, and this can be achieved by lithography, the advances that we make in lithography. So in case of lithography, first we have a wafer along with an oxide layer on top. Then we will be applying the photoresist, and it will be given a soft bake at a lower temperature to remove the excess solvent from the photoresist. And then we will be having a mask. These masks are also known as reticle, and they will be having the pattern that we are supposed to make on the wafer, and it will be aligned with respect to the wafer. And once this has been aligned, we will be developing it by giving UV or visible rays. And photoresist is a such kind of material such that it involves a polymer that changes orientation when it is exposed to light. And therefore what happens, depending on the type of photoresist that will be used, the particular layer of photoresist either becomes more solvent, soluble or less soluble. So in our case here we can say it has become more soluble. So when we add development, that is when we do development, that is when we add a particular chemical, this particular photoresist layer will be lost. And then we do a hard bake to remove the excess solvent again. Then we will inspect such that the pattern has been formed correctly, and we will etch out this photoresist layer and we will strip the photoresist so that on the final wafer we will be getting whatever pattern that was there on the mask. So there are two types of photoresist that will be used. One is positive and one is negative. In case of positive photoresist, if it is used, what will happen? That particular region will be more soluble when it is exposed to light, and it can transfer the pattern directly. In case of negative photoresist, what happens? That particular region will be less soluble when it is exposed to light, and it transfers the negative of the pattern. So then we had spin coating. So in order to make this particular mask, see here we use a mask, right, for giving the pattern. First we need to make the mask that has particular pattern that needs to be transferred onto the wafer. So during mask making, we will be having a substrate, and on that substrate we will be depositing a layer of the photoresist, and we will be spin coating it. And spin coating is done so that we get a uniform thin layer. And during the deposition, first it will be spun at a low rpm and then at a high rpm to get a uniform layer. This is done both in the case of the mask as well as the wafer to apply photoresist. And then electron beam lithography. Electron beam lithography is one another method where we do not require the use of a photoresist. The pattern will be directly given onto the wafer, and this is a high energy consuming process, but it is much more accurate and allows a greater deal of miniaturization. But the process will be expensive. And then we have how to control lithography. So the smaller we can get a feature on the wafer, the greater will be the miniaturization of the device. So that is controlled by this factor, that is sigma. That is sigma is equal to k lambda divided by Na, where k is a constant, lambda is the wavelength of light that is used, and Na is the numerical aperture. The numerical aperture is given by mu sine alpha, where mu is the refractive index of the medium in which this particular takes place, and we have alpha is the half angle of the incidence. So to improve the resolution, so improve resolution means we have to reduce the sigma value. To reduce the sigma value, we can either use a smaller wavelength or we can increase the numerical aperture. So numerical aperture can be increased by using immersion lithography, where this particular setup will be dipped inside the liquid, and therefore this particular value will be increased. So improve resolution, reduce the wavelength. UV and extreme UV lithography can be used. Then increase the numerical aperture by using immersion lithography or by using double patterning. That is, first we will etch off a layer and then repeat the process again to achieve smaller length scales. So that is the recap of the second week. And now we will move on to the question answer sessions. So I hope so far you have got an idea of the second week. So is that clear? Like at least you got a glimpse of what were the contents of week two. Is it clear for all of you? Can anybody confirm? Why aren't anybody coming? You're able to see the presentation, right? Okay, fine, fine. So now we'll move on. Move on to the question answer session. So the quick recap we have already seen in a detailed manner. So diffusion, layering, oxide formation, dry ox and wet ox, thin oxides versus thick oxides, then doping, thermal diffusion and ion implantation, different types of sources, their governing equations and reactions, all those things we have seen. So that's all. And then we have the next is lithography process overview. That is, we saw the positive and negative resist, the processes involved, factors affecting lithography, and so on. So now we'll move on to the practice questions. So the first question is the depth below the surface at which dopant ion concentration is maximum in ion implantation is called. So we just went through the PPT. So can anybody unmute and give me the answer? No, we just saw in the PPT, right? In case of ion implantation, maximum concentration will be at a particular distance below the surface of the wafer, and that particular distance is called as. You can try once more, it's fine. It's not penetration depth, range. Yeah, that's the correct answer. So range is the correct answer. So we'll see what the other things are. So we have four options: range, drive-in, penetration depth, and diffusion length. So range is the maximum concentration below the surface, and next is drive-in. What is drive-in? Drive-in means diffusion of dopants into the wafer. So in case of thermal diffusions, it is characterized by two processes. First process, we will deposit the dopants onto the surface of the wafer. That is the deposition process. Second process is dive-in. That is, we will be providing a very high temperature such that these dopant materials will start moving into the depth of the wafer. So next we have penetration depth. Penetration depth means the maximum depth up to which the dopant penetrates, but it is not the it is the maximum depth, but concentration of the dopants need not be maximum. Actually, it will be much less than at the range. So initially it will be smaller, then at the range the concentration becomes maximum, and at the penetration depth again it will fall. So that is what happens in case of ion implantation. And finally, we have diffusion length. So diffusion length, you might have noticed in case of solid sources when it is used for thermal diffusion, there is a term of root of 4 dt. That is the diffusion length. So for d is the diffusion coefficient and t is the time taken. So we'll move on to the next question now. Which among the following are examples of a solid and liquid dopant source? So your options are ASH3, BBR3, SB2O3, and POCl3. Does anybody know the answer? Which among the following are examples of a solid and liquid dopant source? One of these is solid and one of these is liquid. Which is which? Yeah, D is liquid or solid. Like D is a correct answer, but you need to tell which is solid and which is liquid. Is D a solid or is D a liquid? POCl3. So I guess I'll move on to the answer. So here we have this particular table, right? So there are two types of doping. There is N-type doping and P-type doping. P-type doping means we will be using boron. N-type we will be using arsenic, antimony and phosphorus. POCl3 among this, if you see, is a liquid type. So is that okay? B. B is not the correct answer. POCl3 is liquid and Sb2O3 is solid. BBr3 is also a liquid, but ASH3 is a gas. So this is the thing. When multiple choice questions are there, more than one answer might be correct. So you'll have to give your answer like one is solid, next is liquid, this is again liquid, and so on. So is that clear? Huh. I hope you get it. Like more than one option will be correct. So you need to specify like BBr3 is a liquid, Sb2O3 is a solid, POCl3 is a liquid. Here gas is not mentioned, so we won't consider A option like that. Okay. So now we will move on to the next question. In oxide growth, parabolic rate law is obeyed under what condition? Thin oxide layer, thick oxide layer, when reaction is the rate limiting step, or no oxide layer. Does anybody know the answer? Please unmute. Like two types were there, right? Thick oxide layer and thin oxide layer. One is reaction controlled, one is diffusion controlled. So parabolic rate law is also there, linear rate law is also there. So one is linear, one is parabolic. So which among these is the parabolic rate law? So I think since no one's answering, I'll project the answer. So thick oxide layer. So why is that? Thin oxide layer, as we have already seen, is given by linear oxide growth. And in case of thick oxide, it is parabolic oxide growth. And reaction is the rate limiting step in case of thin oxide. It is not the case of thick oxide. So the option will be B. And the thickness will be 1 to 100 nanometers in thin oxide, and the thickness will be 0.01 to 1 microns in case of thick oxide. So the other options we had already seen during the summary, like growth rate will be constant and thickness is proportional to time in thin oxide. Growth rate decreases with time in case of thick oxide, and thickness is proportional to square root of time in case of thick oxide. So next is more of a memory related question, I would say. If you have watched the lectures, you have already noticed this question. So sir has mentioned in the lecture that a typical thickness value for a field oxide is dash nanometer. 5, 50, 100 or 500. Does anybody know the answer? Like you can give random guesses, it's fine. It's completely fine. Anybody? It's okay to unmute and speak. The answer need not be correct. It's fine. Like unmuting and speaking is not just for the correct answer. It is also to build up your confidence whenever you are asked to answer a question during an interview or any other platform. Just give a random shot. That's all. So anybody has the answer for that question? I think no one's willing to answer, so I'll again project the answer. So, in order to make this particular discussion useful, I urge all of you to ask questions. Otherwise, I'll just go on explaining and projecting the answers, but it won't be of much help to you. Only if you start interacting, then people will start learning more. So, it's better that you can just randomly answer whether it's right or wrong. So in this case, we have a particular table where it gives the thickness versus the application. 6 to 10 nanometer in case of tunneling gates, 15 to 50 nanometers in case of gate oxides and dielectric capacitor gates, 20 to 50 nanometers where silicon oxide pads are made, then 200 to 500 nanometer for hard masks and surface passivation, 300 to 1000 nanometers for field oxides. So in this particular range, only one of our answers will match. So the answer will be 500 nanometer. So please keep in your mind the typical thickness value for a field oxide layer is 500 nanometers. So next is also a question that we have already discussed during the summary. Which of the following statement is true regarding concentration profile with respect to doping from a gaseous source? So in that particular summary, we had seen a column where here there was liquid and there was gaseous sources, and there we had solid sources. Here total profile remained constant. Here surface concentration remained constant in liquid. So which of these will be the answer? For a gaseous source, it has a uniform nature along the depth. It has Gaussian dependence on the depth. It has parabolic dependence on depth. It has an error function dependence on the depth. So, if you might have noticed, you might know the answer to this question. We had discussed it during the summary session. So, does anybody have the answer? Yeah, exactly. Yeah, exactly. That's the correct answer. It has an error function dependence on the depth. That's correct. So we'll move on to the next question. The diffusion coefficient is lower for A than B at the same temperature when activation energy of A is greater than B, activation energy of A is less than B. When activation energies are equal, diffusion coefficient is independent of the activation energy. You will be able to answer this particular question if you remember the equation of diffusion coefficient. So, can somebody give me the equation of diffusion coefficient? Yeah. So based on that, can you now think? Diffusion coefficient is D. D0 is the pre-exponent. It is a constant. So we will not consider that. Same temperature means temperature is also constant. K is also constant. Only thing that changes here is activation energy. That is our EA. So diffusion coefficient for A will be lower than D when activation energy of A is dash than B. So based on that equation, you can think. When EA increases, what happens? The equation is correct. So just yes, exactly. So that's the correct answer. So here see the particular equation is D is equal to D0 exponential EA by KB into T. Here T is constant for both A and D. So we won't consider T. KB is a constant. D0 is the pre-exponent. That is also a constant. So only thing that varies over here is one is D, one is EA. So diffusion coefficient of A is lower than that of D. So D of A is less than D of B, which means that EA should be greater. Since it is an exponent of a negative term, as this particular thing increases, D will decrease. Therefore, activation energy of A is greater than that of B. So I hope that's clear for all of you. So I guess that's it. And now we'll move on to the next question. So in order to grow an oxide layer that is 100 nanometers thick, the thickness of silicon consumed is approximately. This also was given in a particular equation. So using that equation, we know that whenever there is a substrate, there will be an oxide layer on top. So first we have a substrate like this, we have an oxide layer on top, and then we will be having an interface like this. So we will be knowing, suppose this is the actual wafer. Initially the wafer was this much, and to form this much big an oxide, some amount of silicon was consumed. So that is what we are thinking of over here. So the oxide layer D prime is already given to us. So we need to find D. Can anybody tell me what is D? Yeah, that's the correct answer. So that is because this particular thing is D prime is equal to 1.88 D, which means that it will be half. So to grow an oxide layer that is 100 nanometer thick, we need a silicon material of 50 nanometer. So that's the correct answer. So next we'll move on to the section of patterning and layering and so on. So the first question is very simple. The hard copy of the pattern which has to be transferred is known as dash. Reticle, resist, stepper or developer. No. You can try once more. Yeah, that's the correct answer. So the hard copy of the pattern means that this particular pattern is then given onto the wafer, and this particular hard copy or the mask is also known as the reticle. So reticle or a mask will be the answer for this question. That's all. So next is quite like somewhat a lengthy answer for this, but once you know the answer to this, you will be basically aware of the entire lecture. So list the steps involved in photolithography. Can anybody tell me what is the first step or some like array of steps? It may not be in the right order. Can anybody list the steps involved in photolithography? So what do we do for patterning? That is the question. You can randomly try. Like first you need to clean the wafer, then we need to apply so and so, then we need to give light. Like that you can list down the steps. Anybody? Like you can revise through your notes also if you have prepared using the lectures. It's completely fine. You can go through your notes, you can find out, and you can randomly list out. I'll give you like 1 minute time to think. Like what are the basic steps involved in photolithography? The first one will be we'll be having the bare wafer with an oxide layer. So next what will we be doing? Yeah, then, okay, then, okay. Then finally, like it's removed, right? Okay, so like some portion of that was correct. That it was a very good attempt. So thank you. What's your name? Sorry. Okay, thank you, Kriti. And now we will go on to the answer. So thank you. So first we will be having a substrate, that is a silicon wafer, and on top of that we will be having the oxide layer. Then we will apply the photoresist. So photoresist basically is a material that is made up of polymer that is sensitive to light. That is, whenever we give light to it, it will produce certain changes in its alignment. So then what we will be do? We will be having the mask. So mask will be having that particular pattern that we want on the substrate. And this mask will be aligned with respect to the substrate. So this yellow part, see the black part and the yellow part, that is our mask. So once the mask is kept, we will be giving the UV light source, right? So far what did we have? We prepared the surface of the substrate, then we applied the photoresist. Then after applying the photoresist, before aligning the mask, one more step is there. You will have to do a soft bake. That is, bake it at a very small temperature to dry the excess solvent that is present in the photoresist. So after that, we will do the alignment and the exposure part. That is, UV light will be given and after aligning the mask. So once that is done and when the UV light is given, this photoresist will undergo certain changes in orientation, because of which it becomes more soluble or less soluble. And when we are developing it using a particular chemical, this region here, we can say that a positive photoresist was used, right? Because wherever it was covered, that became less soluble. Right. So what we did, we activated it using the light and then we developed it using a chemical. Then what happened? This particular region got etched away. And finally, in order to get the particular pattern onto the substrate, this oxide layer has also to be removed. Then we do an acid bath to remove this oxide layer. And once this entire process is completed, whatever was there on this mask will be transferred onto the substrate layer. And finally, the remaining photoresist, we will strip it off after doing a hard bake. So that is what happens in photolithography. So first we have the substrate, then we do the photoresist coating, then we do alignment and exposure, then we do development, etching, and finally stripping of the photoresist. This is the entire content actually of the third lecture. So if you want a summary kind of thing, there is a figure in our summary notes, as well as you can refer to figure this one. So next we'll move on to the next question. So far we know that a mask will be used in lithography, right? So how do we make the mask? That also involves a series of steps. What are the steps involved in mask making? That is the next question. You can expect questions of like not the entire descriptive question, but which is the step that is used for doing so and so. Those kind of objective questions you can expect from this area. So it's better that you keep an idea of the entire process in your mind. So list the steps involved in mask making. That is the next question. So anybody want to give a try? Like mask will be having that pattern, right? So how do we achieve that? How do we create the mask in the first place? That is the question. Anybody? Or should I give the answer? Like you can just try at least the first step what you will be doing. So I'll give the first step. So if somebody can take a chance from there, that's also fine. First, we will be having a glass or a boron silicate substrate. On that, we will apply a few layers. So can anybody tell me what are the layers that will be applied on top? Anybody? Like if you have taken those down in your notes, you can refer and answer. That's also fine. I guess nobody is answering. So then I'll move on to the answer, I think. So first is you have the glass or a boron silicate or quartz plate will be there. On top of that, you will deposit a chrome layer. A chrome layer will be deposited on top of the glass substrate, and we will keep a drop of photoresist on top of that, and we will spin it. And after spinning, we will be getting a uniform layer. And usually after applying the photoresist, what will we doing? We will etch the pattern, right? We will etch the pattern, and then what happens after etching the pattern? We'll develop the pattern. So this is just a flow chart. I would like you to actually refer to this figure. So first we have the photomask substrate. We have the substrate that is borosilicate or quartz or glass, whatever. And then we have the chrome layer, that is the black region on top. And then we have the photoresist on top. And once the photoresist is right, we will be doing the etching. That is, we will be using a laser beam, and we will be covering like imparting the laser beam onto the surface of this photoresist so that we can get certain patterns. And after we have obtained the pattern, we will expose it to light. Right. And once light is exposed to photoresist, what will happen? This region will become more soluble. And once it has been more soluble, we will do development. That is, we will be adding certain chemicals. And when chemicals are added, this region of the photoresist will be removed. Right. And finally, whatever pattern was there on top of the photoresist will move to the chrome layer. And when the chrome layer is also removed by etching, what will happen? It will get transferred onto the glass or the quartz substrate. And finally, like we did in the previous photolithography overview, we will strip the photoresist, that is the yellow color section will be taken off from the substrate. What happened using a hard bake and then using certain chemicals. So that is how we get the final strip with the required pattern in this region. This mask is then aligned on top of the wafer to get the required IC or chip that we are fabricating. So whenever we are transferring this pattern onto the surface, there are two methods we can do. Either we can transfer the pattern of the same size, or we can transfer the pattern of a reduced size. And this is achieved using stepper machines. So I hope that's clear to all of you. Yeah. So the next question is the process in which unreacted resist is removed after exposure is called. So we applied the resist, we give light to it, it becomes active, then we remove it using a particular process, right? So it was mentioned in that figure. Developing soft bake, alignment or spin coating, the process in which unreacted resist is removed after exposure. That is this particular thing, what happens? So this particular thing has to be removed, right? So what is that process? Whenever photoresist is removed using a particular chemical or something, what is that process called? Any tries for answers? Anybody can try with whatever comes to your mind, it's fine. Like randomly just think. Soft bake means, sorry? Yeah, that's the correct answer. So soft bake, so developing means unreacted resist will be removed. Soft bake means excess solvent will be removed. Alignment means pattern will be aligned with respect to substrate. Spin coating means the process of application of photoresist onto the substrate. So the answer will be developing. So next question is, sorry, which of the following statements is false when using a positive photoresist? So there are two types of photoresist. Can you tell me what is the difference between the two? Anybody? There is positive photoresist and negative photoresist. What is the difference between the two? Yeah. Soluble, yes. So, in case of a positive photoresist, the region that will be covered will become less soluble and the region that is uncovered is more soluble. But when we are using a negative photoresist, exposure to light makes that region more soluble. So, here we will be getting a direct pattern, here we will be getting a negative of the pattern. So, that is the answer to that question. So next is SU8 is an example for, so this is actually 4, this is my mistake. So SU8 is an example for positive resist, negative resist, solvent or developer. Anybody has the answer to that? Just random try you can try. Like I'll give you a clue. It is a resist. Now you can think whether it's a positive resist or a negative resist. Yeah, it's a negative resist. So SU8 is an example of negative resist. So now we will move on to the next question. Which of the following is not a part of the photolithography process? Sputtering, spin coating, baking, exposure. So if you remember the figure, you have a slight idea of the figure, you will be able to answer this particular question. Which of the following is not a part of the photolithography process? No, we actually have two baking processes in photolithography. There is a soft bake and hard bake. Soft bake is for the initial photoresist. Hard bake is actually after placing the mask and etching and exposure. So baking is not the answer. Then you have three trial. Yeah, that's the correct answer. Sputtering. Yeah. Which of the following is not a part of photolithography process? The answer will be sputtering. Is that clear? Yeah. So next we'll move on to the final questions. So this is more of like a problematic thing. For a 248 nanometer laser source, the minimum feature size obtained in air is dash nanometer. So during the last slide for that summary, we had seen a particular equation for sigma. Can anybody recollect that equation? Equation for sigma? Yeah. So for numerical aperture in air is, anybody knows numerical aperture in air? That value will be equal to, so I'll give that hint also. Numerical aperture in air will be equal to 1. And K is a constant which has a value of zero point 0.5. So now can you tell me the answer? Yeah, 124 nanometers. That's correct. So sigma is equal to k lambda divided by Na, where lambda is the minimum feature, sorry, where sigma is the minimum feature size, k is a constant whose value is equal to zero point 0.5, lambda is the laser source wavelength, and Na is the numerical aperture. And numerical aperture is equal to mu sine alpha, where mu is the refractive index and sine alpha is the half angle of incidence. For conventional lithography in air, N is equal to 1. So in that case, if you are substituting all the values, we will get half, zero point 0.5 into 248 divided by 1, which is equal to 124. So that's the correct answer. So next is, what will be the case if immersion lithography is used in the above case? Anybody has any answer? What will be the case if immersion lithography is used in the above case? No, option B, like that's not the answer. Like immersion lithography is used, I can tell you that numerical aperture will actually increase. So the value will be anyway be lesser than 124. So you have two options, 86 and 71. So you can think like that. Like using immersion lithography is actually used for reducing the numerical aperture. So here in the first session we have used air as the medium, right? So in immersion lithography we will be dipping the setup into some other medium like water or oil, and usually immersion lithography is done in water. So what will be the case if immersion lithography is used in the above case? So what will be the value of numerical aperture? Yeah. Yeah, please tell. No. No. So the remaining answer is 86. So I'll tell you how that comes. So for immersion lithography in water, numerical aperture is given by 1.44. So here instead of substituting 1, you will have to substitute 1.44. So zero point 0.5 into 248 divided by 1.44. So you will be getting the answer 86.1111 so on. So your answer will be 86. So is that particular session clear to all of you? Yeah. So that is all the questions that I have for this particular session. If anybody has any doubt or clarity issues or something, we can discuss right now. Anybody has any questions related to this? Because I feel that the lithography part is not very clear to you, how that particular process works. So, no questions for anyone? I think nobody has any questions. Yeah, yeah, sure, sure. Okay, short summary, fine, fine. So actually, every week in NPTL, okay, every week in NPTL, they will be floating a particular PPT like this. So that particular PPT, is this visible to all of you? Yeah. So in this particular PPT, whatever content that has been discussed in all the 3 weeks will be given. So for example, in last week, oxidation, doping, and lithography was discussed. So main points in oxidation like dry ox and wet ox, what is that? That equation that we used for solving the session, D prime is equal to 1.88D, all those things, the particular figure that was used, and the oxide regimes that we discussed, thin oxide versus thin oxide, parabolic grade growth comes in thick oxide, thickness is proportional to time, the difference between these two, all of this is given in the first part of the summary. And then we went on to doping types. Doping types will be of two types, thermal diffusion and ion implantation. And this forms the second lecture of week 2. Thermal diffusion is a high temperature process. Ion implantation is a low temperature process. Here we can say concentration is maximum at the surface. And in ion implantation, concentration is maximum at a particular distance known as the range. And moving on, we had seen in case of thermal diffusion, this particular equation we had used for solving a question, that is D is equal to D0 exponent EA by KB into T, where D0 is the pre-exponent factor, EA is the activation energy, and KBT is where KB is the Boltzmann's constant and T is the temperature. And while substituting in such kind or any kind of equations, please be careful that you substitute in the same unit. Otherwise, you will be getting a different answer, and that wrong answer will surely be there in your options also. So please be careful. And then we have in thermal diffusion liquid and gaseous sources as well as solid sources. So solid sources, I had one particular question for you, which follows a Gaussian solution. So two equations will be governing that to find the concentration at a particular depth and the time taken to achieve that concentration. So this is at the surface and at a time t, and this is at a depth of x at a time t. So these will be the two equations. So in case of liquid or gaseous sources, we have a surface concentration Cs, and the solution is given by an error function solution. So this is the surface concentration, and using these values, diffusion coefficient, time, and the depth, we will be able to find the concentration profile. So after that, we went on to discuss about ion implantation in that lecture, whether it's a lower temperature process and high energy ions will be impinging, maximum concentration occurs at the range, and after implantation, we need to activate the dopants. And this particular thing is discussed in lecture 3, and everyone please be very clear with this process, because number of questions can come from each of these steps. So first we have the wafer. The wafer will be having an oxide layer on top, and we will be applying the photoresist. Photoresist is applied using the spin-on process. Spin-on process means that initially a drop will be placed, it will rotate at very low RPM, then after a certain time it rotates at a high RPM so that we will be getting a uniform layer. And then we will do a soft bake. This photoresist will be having solvent in it since it is a polymer solution. So we need to remove the solvent, right? So we will be doing a soft bake. So after the soft bake, the solvent will be removed, and after that we bring our mask. This mask has particular pattern that we need to transfer to the wafer. We will align it with respect to our wafer, and we will expose it to UV or visible. There are even materials that are and like active with respect to X-ray or whatever material you are using. So usually the thing is we will be using UV light or visible light, and after that is done, based on the type of photoresist that is used, whether it is positive photoresist or negative photoresist, that region becomes more soluble or less soluble. In our case, it has become more soluble. So when we do development, that is when we add a certain set of chemicals, this particular region will be removed. So now this region is not there, and the pattern from the mask is transferred onto the surface of the oxide. And then we will do a hard bake to remove the excess solvent from this layer of photoresist. And finally, we will be inspecting. So here it is actually reversible. Up till this process, it is reversible, right? Our wafer is still in good condition. So here we will do inspection, make sure that the pattern is correctly transferred onto the oxide layer, and then we remove the oxide layer also by using etching. And once that is done, the pattern will actually be on the surface of the wafer. And what we will be do then, the remaining photoresist will again be dissolved by using certain chemicals. And then we have our final wafer with the pattern on the top. So this is the lithography process overview. And like very detailed explanation is given in lecture 3. Please go through the lecture. So yeah. Then positive photoresist versus negative photoresist. Positive photoresist means when light is incident, it becomes more soluble and there is a direct transfer. Whatever is there on the mask goes directly. Here, whatever was there on the mask, the negative of that will be transferred. It becomes less soluble when exposed to light. That is there. Then we had spin coating. Spin coating is used for applying this photoresist. Initially, small quantity will be applied. It will rotate at low RPM to spread it, but you can see that the surface is not very even. So we will rotate at a very high RPM to get a uniform surface. So, and whenever you are applying a photoresist in a laboratory, please be sure that it covers a certain region on the wafer. Like it should not be too less, it should not be too much. It should be exactly at the center of the wafer and sufficient quantity should be there. And then we have electron beam lithography. Like this photoresist application is like somewhat time consuming and tedious, and more than that, it requires a certain level of skill to get it correctly. So beam lithography is another process that is quite expensive, but it can directly use for transferring pattern using an electron beam. So that is the case. So then we saw the final question that we had discussed, that is sigma is equal to K lambda divided by Na, where here it is the size that can be obtained. K is a constant, lambda and numerical aperture. So in order to improve the resolution, you can reduce lambda or increase Na. Na can be increased by using immersion lithography. That's all. So is that clear for all of you? Like just a recap of whatever was there in week 2. I hope you got an idea. Yeah. So now if you have any other additional questions or anything, you can post it directly in the discussion forum, or you can email me. And people who are planning to write the exam, please register for the exam. The last date will be on 15th, so you have roughly less than 1 week, I think. So if you are facing any technical difficulties, please email NPTEL team directly. Do not delay, because you will be losing a chance to write the exam. And I think the 10th, this coming Wednesday, is your day for submission of assignments, right? Like two sets of, yeah. It will be like most probably it will be objective type only. Descriptive questions won't be there. Like whatever we are discussing during these live session, right? Optional questions or maximum fill in the blanks. That's all. But you need to be familiar with the entire content, because sometimes these options can be very confusing. Yeah. So that's the case. So have you started attending your assignments? So if not, I please urge you to start doing your assignments, as you have to submit them on the 10th, that is tomorrow. So many questions, whatever we have discussed so far and whatever is given during class is actually overlapping. So please take your time to do your assignments. So that's all for this week. Any other questions from anyone? I hope not. Nobody is responding. So thank you everyone for your time. And so see you next week. Please do join at 6 p.m. sharp. We will be discussing the patterns that is related to the third week actually. So see you next week. Thank you very much. Yeah. Thank you so much. Yeah.